Hi. With this video, I want to talk a little bit about PSHA results looking at sensitivity studies. And I'm going to show you a series of figures that kind of look like the lower left one here, where we're going to vary some part of the inputs and understand what that does to the output ground motion hazard. Okay. So this first one, and I should say kind of all of these are going to use as the baseline, the Gutenberg-Richter example from the prior videos. So we've got Mmax of 8, Mmin of 5, B of 1, 0.05 earthquakes ruptures per year. I think that's supposed, and the distance is 10 kilometers from the site. So it does the same parameters we've been working with a bunch in the Gutenberg-Richter examples. And then I'm going to vary something in each one of these slides and see what happens to the ground motion detectors. Okay. So let's take a look at this. So in the first, as our baseline, we've got the dark blue line here. So this is just say baseline, where we're going to keep that line in the same spot always. In this case, what we're going to do is we're varying the rupture rates by a constant. Okay, so the red line here, what we did is we said all of the rupture rates are going to get doubled. So all the earthquakes are twice as frequent. And in the light blue line, we've got all of the earthquake ruptures are half as frequent. They're multiplied by 0.5. Okay? And so that's the change. And what we can see is if I've got the PSHA equation shown over to the right. So if we have this baseline rate of ruptures over here that we had used in our previous calculations, thinking about like the red case, what we did is we just put a 2 in front of all those rupture rates, right? We doubled them all. And it is just a summation. So the 2 is going to come outside. It's just a constant in all our terms. And so we can see that all the rates are just going to be doubled, right? So all of the rates go up by a factor of 2. And if we cut the rates in half, they all go down by a factor of 2, right? And then log scale up or down by a factor of 2 shows it's the same distance. So we can see that kind of linear offsetting. Okay, so that's a nice easy one to get warmed up, right? Any change in earthquake activity rates changes the ground motion hazard curve proportionally. That should be intuitive. Suggests we need to understand our earthquake activity rates because obviously they're going to translate directly through into the rates of IM exceedances. Okay, next one. Let's take a look at this one, maybe a little less intuitive. Now we're going to think about the Mmin, right? So what's the value of Mmin? And we talked about previously that Mmin is not a physical constraint on earthquake occurrences. It's just the minimum magnitude that we find to be of interest in our analysis, right? So in our baseline analysis, the dark blue, Mmin was 5. And here we're going to vary it. We're going to increase it to 5.2, 5.6, or 6, and so on. And for reference here, I've got the original calculation table shown over on the right. So we had the magnitudes from 5 up to 8. We discretized them, and we've got the midpoints indicated with the MI column here. And we've got the rates of the ruptures and the probabilities of exceedances and so on. Multiply those out, add them up, and we got the 0.00212 from our previous results. If we set the Mmin equal to 5.2 instead of 5.0, what effectively we would do is we would just get rid of this top row. Say, I'm not interested in the values from 5 to 5.2, so I can get rid of that first bin, and I'll just start at 5.2, moving on, and the midpoint would be the 5.3, that lowest one. So if we do that, and this table, this is shown for the 0.2G case, we see that the contribution over here on the right side was a pretty small number, a 10 to the minus 5, and we've got lots of numbers that are like 10 times bigger here. So if we look at 0.2G here, which the table is showing results for, that has a negligible effect, right? If I move from the dark blue line to the red line, it doesn't make any difference here because and maybe the easiest part we can see here is that even if those earthquakes were to occur, and they occur pretty frequently, they have less than a 1% chance of causing an exceedance of 0.2G. So whether we include them or not doesn't make any numerical difference. Right. As we move down to very small spectral accelerations at the very far left side of the plot, there's a small difference. But as we move to larger 0.1G and above, there's basically no difference between the dark blue line and the red line. Okay, we could move on to higher Mmin values. If we moved up to 5.6, that would have the effect of kind of crossing off the next 2 rows. We would start our calculations at 5.6 instead. That has a more substantial effect, and even up at 0.2, we can see the difference in the lines, but it's not very big. At the lower intensity levels, it does make a difference because we cut out a bunch of these frequent earthquakes that do have a chance of causing an exceedance, and so on. We can go up to 6 and start seeing things drop off. So first of all, we see that over at the larger ground motion amplitudes, there's no difference here, really, because it takes pretty large magnitude earthquakes to get those events occurring. And even at 0.2G or so, there's very little difference for kind of Mmin less than 5.6 or something like that. At some point, we'd start to see a difference. If we have Mmin of 6, we can see a little bit of a difference there. But so this helps us to understand that this Mmin value is really a choice of convenience. And in terms of this particular problem, we could look at a sensitivity study like this and see, depending on the spectral acceleration amplitudes we were interested in, we may or may not need to adjust that Mmin value. But we can see really very little sensitivity up at the higher ground motion levels. And so this is the type of quick check you could do to check on your Mmins. And this is really where the convention of Mmin of 5 or Mmin of 4 comes from, is from general studies like this to see that going to lower magnitudes oftentimes doesn't have any real impact on these hazard curves. Okay, so that's Mmin. Here's a study on Mmax. So we do the same type of calculation. We have Mmax as 8 as our default with those calculations. So that's, in this case, black is our default value. If we drop that down to 7.8, we're doing the same type of thing. We're going to ignore all the values between 7.8 and 8. So in this case, I'll drop that off. And again, that's not this is the 0.2G case. That doesn't make much difference. So at 0.2G, we can't see any sort of difference, whether we include those or not. And in this case, it's not so much because of the probability of exceedance of the ground motion. It's because the earthquakes are very rare, right? So I have a very small earthquake occurrence probability. So whether I include it or not is not making a very big difference in my overall occurrences, right? There's lots of more frequent earthquakes that have a pretty good chance of causing an exceedance. And so those ones are really going to be the most important for my hazard calculation. This very largest magnitude is not so important. So this one's kind of interesting because the Mmax is not a choice of convenience. This one is one that's constrained by the physical situation we're dealing with. A couple thoughts here. So one, this result here is with the truncated Gutenberg-Richter relationship. If we used a characteristic relationship that had a significant probabilities of occurrence for the characteristic large magnitude earthquakes, this story could look different, right? And so we would need to do a separate sensitivity study there. Those large magnitude earthquakes could be pretty important if they had high probabilities of occurrence. The second thing that's interesting here is that we see this is a case where I varied Mmax, but I didn't change the overall rate of Mmin earthquakes. And so we've got a fixed rate of small earthquakes, and it's just a question whether we include the large earthquakes or not. But you might remember from our earlier calculations of moment rate that those big large magnitude earthquakes are really important for moment rate. So if we don't have the magnitude 8 earthquakes and we need to balance our moment rates, all the other events have to get a lot more frequent. And so we could imagine dropping the Mmax here is not showing much difference in the hazard curves. But if we had to make all the earthquakes more frequent, now we're back to the first slide in the video where the increased rate of events is going to drive up the hazard curve. So it turns out that when we're trying to balance moment rates, a smaller Mmax may actually give us higher ground motion hazard. That's an interesting thing that we can explore outside of the videos. Okay, so that's Mmax. Last one to look at is the ground motion model sigma. So this is the standard deviation in the ground motion model predictions. So let's talk this one through. This one's probably the least intuitive, but I've got some backup results to help us understand. So what I've got is in the dark blue line, this is our baseline again. We're going to do all the calculations as per standard. And what I've got indicated in the legend is that the standard deviation for the ground motion model is just the original standard deviation, so 1 times that. In the red, what we've got is a calculation where the standard deviation for the ground motion model is only 0.6 of the reference standard deviation. And maybe I should label that in. This kind of sigma on the right-hand side is the reference standard deviation. So that's like the real value that was published. Okay, so with the red line, we're going to use a value that's only 60% of the published value. And in the light blue line, we're going to use a value that's only 10% of the published value. So we're reducing that ground motion variability. And you get the ground motion hazard curves are dropping here in that figure. Probably not immediately obvious what's going on. So let's talk this through. So one thing we can look at here on this slide is that, again, looking at the 0.2G spectral acceleration values here, the probabilities of exceedance, right, they're coming up and up somewhere around like 6.5 to 6.7 is where we see about a 0.5 probability of exceedance, right? So for the smaller magnitudes, we've got lower probabilities of exceedance, and for the larger magnitudes, we have bigger than 0.5 probability of exceedance. So to think this through a little bit more, here's a couple more figures to help us. So the left figure is showing, and this is all the Bohr, Joyner, Fumal 1997 ground motion model. Let's note that. Same as on the previous slide. So in the black line, we've got the mean of the prediction, or the mean of the prediction of the log SA. And then in the dashed lines, we've got plus or minus 1 standard deviation. So the dark blue, this is the reference. And then in red, we've got 0.6 times the reference standard deviation. And then in light blue, we've got 0.1 times the reference standard deviation. So it's real nice and narrow there. So what's going on? The ground motion model is telling us the distribution of ground motion intensities associated with a given magnitude. So the magnitude is on the x-axis. And then implicitly, the distance was 10 kilometers for all cases. That's where the site was in this case. Right, so when I think about the dark blue line, we can think about say like a magnitude 6 earthquake. And we know that the mean of the distribution in log SA in this vertical axis is log scale. That's going to be right at that black line. And then the standard plus or minus of standard deviation incorporates about 2/3 of the probability. That's our reference rule of thumb for a normal distribution. So probably something like this is going to look like our distribution from the dark blue line. And then if we want to exceed a 0.2 G, that's our kind of reference number from the table, we've got this probability here that's shaded in. If I stagger a little bit to the right, just so we can see what's going on, maybe I'll go like 6.25 or something like that for the light blue line. Right, so we know that the mean is at the black line, and then the plus or minus standard deviation for the light blue is very tight. So it's going to be very narrow, and it's going to be very hard to get an exceedance of 0.2 G for one of these smaller magnitudes. On the further to the right of the plot, the situation is going to be flipped, where for the small standard deviation, we're almost certain to have an exceedance of 0.2 G, like the whole thing's going to be an exceedance. Versus with the reference published standard deviation, we'll have a much flatter distribution, and we're not going to be certain to exceed that 0.2 G, even at a large magnitude, right? And so those shaded areas, that's what's plotted over here on the right. So I've got magnitude plotted on the x-axis, once again, so same axis is on the left. And the vertical axis is going to be the probability of exceeding 0.2 G given that magnitude. Right? So I'm just plotting out these shaded areas. At the risk of getting a little messy here, so maybe magnitude 6. Got a 10% probability of exceedance. That's this shaded area here. Will be this 0.1. And then I've got, say, a magnitude 7.5 or so plotted. This shaded area is going to be somewhere like a 0.9 or something like that. So you can see that as we move left to right in magnitude, the dark blue case, we're going to move up in probability, but slowly because of the wide variability in the ground motion model. If we suppress the variability in that ground motion model, like in the light blue case, we have much more of a step function in probability. And once we get to 6.6 or 6.7, our probabilities of exceedance are going to go very quickly from almost 0 to almost 1. Right? And you can see they're all pivoting around a point where the median ground motion model is, where the median hits 0.2 G. On the left figure, that looks like it's somewhere around 6.6 or 6.7. And so we've got this kind of symmetry around 6.6 or 6.7 in terms of these probabilities of exceedance. But remember Gutenberg-Richter relationships. So the Gutenberg-Richter relationship says that low magnitude earthquakes are much more frequent than high magnitude earthquakes, right? So a magnitude 6 is 10 times more likely than a magnitude 7, roughly speaking. And just the fact that I've got this kind of pivoting in these probabilities, where the probabilities go down when I've got lower ground motion model standard deviations, the probabilities go down for low magnitude earthquakes and go up for high magnitude earthquakes. That means I'm actually going to have lower ground motion hazard because all those frequent magnitude 6 earthquakes, I no longer have exceedances. For the 7s, I've got a higher probability of exceedance, but those are much more rare than the magnitude 6s. So the impact from the left-hand side of this plot is really much, much bigger than the impact from the right-hand side of the plot on ground motion hazard. Okay? So let's go back to the previous slide and think that through now with our context. Thinking about the probabilities of exceedance for spectral acceleration of 0.2 G, this kind of middle row in the table. all these values of probabilities that are less than 0.5, all the values less than 6.6 or 6.7, these probabilities are all going to get smaller when the standard deviation is reduced. So if I have less variability in my ground motion model, I don't predict any, I'm going to predict smaller probabilities that those small magnitude events could produce a big IM. The lower values, these are going to get bigger, but they're rare, right? The rates of occurrence are pretty small. And so the overall effect is, if I come back over to 0.2 G on the left-hand side, my ground motion hazard goes down when my standard deviation of my ground motion model goes down, okay? And that's consistent for all at IM levels, right? So no matter how small I get, you might say, what about these small IM levels? That's going to, even the small magnitude earthquakes are going to cause exceedances, but there's always smaller magnitude earthquakes, and there's no sort of like counterbalancing effect here, right? If we ignore or we underestimate the ground motion model standard deviation, we get lower ground motion hazard. The effect gets particularly pronounced for high IM levels. You can see out at the end on the right-hand side, there's a really big drop-off because at some point, even the largest magnitude earthquakes need to be above average in order to cause an exceedance. And so the ground motion model sigma has the same effect in every single magnitude. And so we get these big drop-offs. Okay. So that one's a little bit more of a head scratcher probably than the other ones. And it takes a little bit of thinking to think through what it is, but hopefully my diagnostic slides helped you a little bit with that. And this points to a kind of a practical challenge that we see very frequently in these real world hazard studies, which is that the ground motion model standard deviation is a really important parameter. There is very big variability in real world ground motions. Those standard deviations are large. And if we don't recognize that full large standard deviation, we can underestimate the possibility of small magnitude earthquakes causing a big ground motion, and thus underestimate our ground motion hazard. So a little bit of a story on this last one, but this is an important issue. And when you see real world hazard studies, you see a lot of debate about standard deviations in the ground motion models, and hopefully you got a little flavor here of why. Okay, so that explains some kind of key sensitivity studies. Very easy to do these types of studies with other types of parameters and get a broader understanding. To some extent, these sensitivities are also case specific, so it depends on what kind of sources you have around and things like that. But I tried to pick some cases where there's a general finding here that'll hold up in a range of cases. And so hopefully that starts building your intuition. Okay, so that's it for this video.